ever try to figure out what shape something is by, like, smashing it to pieces? Sounds kind of crazy, right?
Yeah, a little destructive.
Well, that's what scientists at Brookhaven National Lab are doing, but with atoms.
Yeah.
They're smashing atoms to figure out the shapes of atomic nuclei.
It's pretty wild stuff, and we've known for a while that the shape of these tiny nuclei really affects how atoms behave. It affects things like nuclear reactions, the formation of elements.
Wow.
Even the conditions of the very early universe.
So it's not just like some theoretical physics concept. It has real implications.
Oh, yeah, absolutely. I mean, think of it this way. The nucleus is like the blueprint of the atom.
Okay.
And its shape dictates how that atom's going to interact with other atoms and how it's going to behave in different situations.
Gotcha. So how do scientists actually, like, figure out the shape of something that tiny?
Well, for a long time, we were stuck with these low-energy methods. It was like trying to see a moving object with like a blurry, long exposure photograph. You could get a sense of its outline, but no real specifics.
So what changed? How are they getting a clearer picture?
They're using this thing called the Relativistic Heavy Ion Collider, or RHIC.
Okay.
Basically, it smashes atoms together at super high speeds. And by analyzing the particles that come flying out from these collisions, like their direction, their momentum, they can actually reconstruct the shape of that original nucleus.
So they're like atomic forensic scientists. They're using the debris to figure out what happened.
That's a great way to put it.
Cool. So are they actually getting good results with this?
Amazing results. They recently smashed gold and uranium nuclei.
Okay.
And what they found is really cool. We already knew that gold nuclei are spherical.
Like little marbles.
Exactly. And uranium nuclei are elongated like little footballs.
So they were testing their method.
Yeah, and the results confirmed everything.
Interesting.
With gold, they saw a consistent pattern of particles flying out, which you'd expect from a sphere. But with uranium, there was more variation, which you'd expect from that elongated shape.
Cool. So this new technique seems to be working, but why go through all this trouble just to study the shapes of these nuclei? What are they actually trying to solve?
One of the big mysteries is the quark-gluon plasma.
I've heard of that.
This is a state of matter that existed just after the Big Bang when the universe was super hot and dense.
So they're recreating the Big Bang?
In a way, yeah.
Yeah.
And the shape of the colliding nuclei actually affects the shape of the quark-gluon plasma.
Wow.
Giving us clues about those early conditions.
Okay, I see the connection there, but what about the real-world applications? You mentioned nuclear reactions and the formation of elements.
Right. Well, the shape of nuclei is super important in nuclear fission. The process that powers nuclear reactors.
Right.
And, well, certain other things.
So understanding the shape could help us control these processes better.
Absolutely. It's all about understanding how nuclei behave under different conditions.
Makes sense.
And then there's the formation of heavy elements in neutron star collisions.
Neutron stars. Those are the super dense remnants of collapsed stars, right?
That's right. So dense that a teaspoonful would weigh billions of tons.
Crazy.
And the shape of the nuclei in those collisions directly affects how heavier elements like gold and platinum are created.
Whoa. So by smashing atoms, we're not only recreating the early universe, but also understanding how the elements that make up our world came to be.
Yeah, it's remarkable.
Yeah.
But what's even more exciting is that this new technique is revealing details we never even suspected.
Oh.
Like what? Well, we used to think of uranium nuclei as simply elongated, like those little footballs we talked about.
Yeah.
But the data from RHIC suggests they're way more complex than that.
Interesting.
And this has some really interesting implications for a specific type of nuclear decay called neutrinoless double beta decay.
Neutrinoless double beta decay. That sounds complicated.
It is a bit, but it has the potential to like revolutionize our understanding of physics. And the shape of those uranium nuclei might hold the key to understanding how this process works.
Okay, I'm definitely intrigued. But before we dive into that, I think we need to make sure our listener is up to speed on double beta decay in general. Can you give us a quick rundown of what that is?
Of course. Imagine you have two neutrons in an atom's nucleus.
Okay.
In double beta decay, those two neutrons decay at the same time into two protons, releasing two electrons and two antineutrinos in the process.
Okay.
It's pretty rare, but it's been observed in a bunch of isotopes.
So two neutrons become two protons plus some other particles.
Got it.
But what makes this neutrinoless version so special?
Well, in neutrinoless double beta decay, if it actually exists, those two neutrons would decay into two protons and two electrons, but no antineutrinos would be released.
And why is that such a big deal?
because it would mean that our current understanding of particle physics is like incomplete. It would violate a fundamental principle called lepton number conservation.
Okay, now you're going to have to explain that one. What is lepton number conservation, and why should I care if it's violated?
Think of it this way. Leptons are a family of fundamental particles that include electrons, muons, tacits, and their corresponding neutrinos.
Okay.
According to the standard model of particle physics, the total number of leptons in a closed system should always stay the same.
So it's like a cosmic accounting system. You can't just create or destroy leptons out of thin air.
Exactly. But if neutrinoless double beta decay were to happen, it would be like having those leptons disappear without a trace.
Oh.
It would be a major discovery, potentially pointing to new physics beyond the standard model.
Wow, that's a lot to wrap my head around, but I'm starting to see why scientists are so excited about this. So how does the shape of the nucleus tie into all of this?
Well, this new imaging technique can be used to study something called isobar nuclei,
Okay.
which are pairs of nuclei that have the same total number of protons and neutrons, but a different distribution of each.
Uh-huh.
These isobar pairs are often involved in double beta decay processes.
So by understanding the subtle differences in shape between these isobar nuclei, we can gain insights into the mechanisms behind double beta decay and potentially even neutrinoless double beta decay.
Exactly. It's like having a more detailed map of the terrain,
Right.
allowing us to better understand the paths that these nuclear reactions can take. And this is where the shape of uranium comes in.
Okay, so it sounds like we're about to get into some really exciting territory. But for now, I think we need to give our listener a moment to digest all of this amazing information. We'll be right back to delve deeper into the world of neutrinoless double beta decay and what it could mean for our understanding of the universe.
So, before the break, we were talking about this new technique for imaging atomic nuclei
Yeah.
and how it's helping us solve some of the biggest mysteries in physics.
Right, like is there new physics beyond the standard model?
Exactly. And remember how we were discussing neutrinoless double beta decay?
The one where 2 neutrons decay and no antineutrinos are released.
Right. And the shape of uranium nuclei might be the key to figuring that out.
So how does that work? You mentioned that this new imaging technique can be used to study isobar nuclei.
Yeah, so isobar nuclei have the same number of protons and neutrons.
Right, but they're arranged differently.
Exactly. And these isobar pairs are often involved in double beta decay processes.
Okay.
And by understanding the subtle differences in their shape, we can get a better understanding of how those decays work.
So it's like having a more detailed map.
Yeah, like a map of the landscape, allowing us to see all the different paths that these reactions can take.
I like that analogy.
And when it comes to neutrinoless double beta decay, the shape of the nucleus could really affect how likely it is to happen.
Interesting. So the shape of the nucleus could actually determine if this physics-breaking decay happens or not.
It's possible.
Yeah.
You see, the shape of the nucleus affects how the protons and neutrons are arranged inside.
Okay.
And that arrangement influences how strongly those particles interact with each other.
And those interactions are what govern these decay processes.
Exactly. And if the shape of the uranium nucleus is just right, it could make neutrinoless double beta decay more likely.
So we could be talking about rewriting our understanding of physics, all thanks to the shape of this tiny nucleus.
It's pretty amazing, right? And observing neutrinoless double beta decay would have huge implications.
Like what?
Well, it would challenge what we know about particle physics and could point to new particles or even new forces.
So a whole new world of physics beyond the standard model.
Exactly. It could help us understand why there's more matter than antimatter in the universe.
Wow.
Or even give us clues about dark matter.
It's crazy to think we started talking about smashing atoms to see their shapes, and now we're talking about the fate of the universe.
It just shows you how powerful fundamental research can be.
Right, you never know where it might lead.
And in this case, it's led us to the very edge of what we currently understand about the universe.
Right.
But hey, remember how we were talking about the formation of heavy elements in neutron star collisions?
Yeah, you said the shape of the nuclei involved affects how elements like gold and platinum are created.
Right. And this new imaging technique could give us a much better look at how those processes work.
So we could finally understand how the elements in our world were created.
Exactly. And this research could also have practical applications too.
Like what?
Well, think about nuclear energy. Understanding the shapes of nuclei could lead to safer and more efficient nuclear reactors.
So this research has implications for both the origins of the universe and the future of energy production.
It really does. It's a truly interdisciplinary field, bringing together all kinds of physicists.
So high-energy physicists, nuclear physicists.
Astrophysicists, you name it.
It's amazing how collaboration across different fields can lead to such incredible discoveries.
Absolutely. And this is just the beginning. This imaging technique is going to keep on surprising us for years to come.
So what's next for researchers in this area?
Well, now that they've shown that this technique works, they're going to want to use it to study a bunch of different nuclei.
Makes sense.
I mean, there's a whole periodic table out there.
So many possibilities.
Yeah, they'll probably focus on nuclei that have been difficult to study in the past.
Like ones that are really unstable or have very short half-lives.
Exactly. It's a really exciting time to be a nuclear physicist.
For sure. And the things we learn from these experiments will really change our understanding of the universe.
From the smallest particles to the largest structures.
It really is amazing. And it reminds us that science is all about discovery.
That's right. And that searching for knowledge can take us to some pretty incredible places.
Well, I can't wait to see what they discover next. But for now, I think we should take a moment to let all of this sink in.
It's been a lot to process.
We'll be right back to finish our deep dive into the fascinating world of nuclear physics. So we've talked about how this new imaging technique can help us understand the quark-gluon plasma and the formation of heavy elements.
Yeah, and even the possibility of physics beyond the standard model.
But I'm sure there are other things we haven't even thought of yet.
Oh, absolutely. I mean, we can see the shape of nuclei now with amazing precision.
Right.
It's like we have a new way to look at the subatomic world.
Yeah, like a brand new set of eyes.
Exactly. Who knows what we'll find?
It really is like exploring a whole new world.
And every time we look closer, we find more details, more questions.
It's amazing.
That's science for you. Always exploring and discovering new things.
And this new technique is a powerful tool.
It really is.
We're not just seeing the shapes of nuclei.
Nope.
We're seeing the fundamental forces and processes that govern the universe.
It's a total game changer. And it really shows you that even the smallest things can help us unlock the biggest mysteries.
Like those tiny nuclei.
Yeah, exactly.
So where do we go from here? What other secrets are waiting to be discovered?
Well, scientists all over the world are trying to answer that question.
I bet.
We'll definitely see new experiments pushing this technique even further.
And maybe someday we'll be able to see more than just the shape of nuclei.
Right.
Maybe we'll see the quarks and gluons moving around inside.
It's possible. Or maybe we'll even find those new particles beyond the standard model.
I can't wait to see what the future holds for nuclear physics.
Me neither. The possibilities are endless.
But the most important thing is to stay curious, right?
Oh, absolutely. Keep asking questions and keep exploring.
Because the universe is full of amazing things just waiting to be discovered.
Well said.
Well, I think we've given our listeners a lot to think about today.
For sure. From smashing atoms to the shape of uranium nuclei, it's been quite a journey.
It really has. And maybe this deep dive has made you curious about the universe, too.
Maybe you'll look at the world a little differently now, knowing that everything is made up of these incredible structures.
So keep exploring, keep asking questions, and never stop wondering.
The universe is waiting.
That's it for this deep dive. Thanks for listening.